So before we've seen RNS geometry. So this is a different type of stereochemistry where we assign some sort of configuration, but it's not RNS, and it's called EZ. And it is pretty easy. So essentially what you want to do is whenever you see an alkene or some sort of pi bond, you draw this kind of like dotted line through that bond, literally right through it. It's always parallel to that bond, okay? And then we're going to look at the substituents that are on opposite sides of that line, but one carbon at a time. Does that make sense? So essentially, let's look at this one carbon at a time, and then assign priority to the substituents on both sides of this line. So out of it looks like sec-butyl or an isopropyl group, which one is higher priority? Well, it looks like the sec-butyl, excuse me, would be the highest priority because there's more carbons and it's more complex than the isopropyl. And then it looks like on this side, you know, in terms of this carbon now, we have this amino group or we have this kind of propyl group. So because nitrogen is before the carbons, priority here, priority here. So the priority assignments are the same as we've seen before with doing it based on atomic number and complexity, the exact same thing. But we're doing it now one carbon at a time with respect to the substituents on either side. And you have to do it for both carbons, okay? So essentially, oh, I'm sorry, I wasn't looking closely. And yes, I see in the chat box. Yep, yes. I saw that in the chat box. My bad. You're right, CCC versus CHH, that's correct, okay? So it should be this. So again, C, and an H, C and HHs, okay? So this one, you're totally right. This should be 1 and that should be 2. This should be 1 and that should be 2, okay? So once you do that, that's like the first step. Then you have to see, are my highest priority groups on the same side or are they on opposite sides? So by that, I mean, with respect to this dashed line, are all the 1s on one side and all the 2s on the other side? Or do you have like 1 up here, 2 over here, 1 up here, 2 over here, or like, you know, diagonal things? And we clearly see that we have all the 1s on one side, all the 2s on the other side. So that is the same side. So same side is Z. Okay, and this comes from like some German word called like Zwazmen, something like that, something crazy like that, and it means same, it's like same side. So Zwazmen, and yeah, that's what I've always said, like same side. So Z is for the same side. Great, that's literally how I've done it too. But yeah, it's from German and it's Zwazmen, something like that. Okay, so that's Z geometry. So E geometry would be an example like we're gonna see here in 1B. Okay, so for 1B, we see that we have a structure that looks like this. Pi bond is here, and 2. Okay, so then do that same thing, draw this line. Okay, I'll draw in the hydrogen just because it's the other substituent that I'm comparing it against. And essentially, I'm going to do that same sort of priority thing. So from this one carbon, I see on this side I have some carbon atoms, and on this side I have a hydrogen. So that's easy. 1, 2. Okay. So then at this carbon, now we're looking at carbon sulfur or carbon oxygen. So we know sulfur is higher priority. So 1, 2. Okay. So now, based on those assignments, are the 1s on the same side and are the 2s on the same side? No, they're on opposite sides. So E is the assignment that we give to it, and it stands for like opposite is like entamen instead of like Zwazmen, it's like entamen or something like that. I have no idea, something crazy like that. But so E means opposite sides, Z means same sides. I'm gonna keep saying that, same sides. I like that. Okay, so it's just like another type of RNS, but like we use E and Z essentially. Why is it wrong to CHH versus COO? Are you looking at CHH versus COO? Yeah, because Abby, if you did CHH versus COO, then you would get opposite priorities, because that COO would clearly take higher priority. So that is wrong. Why was the 1 versus 2? The 1, are you talking about the 1 for the sulfhydryl group, Charles? Oh, you saw it, awesome, okay. And Abby for B. So you're looking, Abby, you're looking here and you're doing COO. Is that what you're doing? Yeah. So essentially, you know that it's CS. Like that's like what I'm thinking. Like I just do CS and I see CO. And the first point of difference is the sulfur versus an oxygen. That's how I do it. Okay. So that's why I picked that one. Okay. Yes, the S is directly connected. So yeah, Mary, that's great. That's probably why I also assigned that to be 1. Yes, and it's still based on atomic number. Everything's the exact same. We're just not doing R and S. We're just doing E and C, if that makes sense. In a different version. You're not dumb. No one's dumb, but I'm good. Okay, so that's 1A and 1B. Let's keep doing this. Let's see. 1C. Okay, so 1C looks a little bit crazier. So you guys can see it, and I think this is the last example we'll do. It's not too terrible. It's just the same thing that we've seen. And I want to get into real reaction stuff because that's cool. Okay, so again, with respect to this bond, we're gonna look at both sides. So I think this is pretty obvious, right? So you guys can see we have either these carbonyls, actually specifically this amide and this aldehyde on both of these sides. And this one is going to be 1, clearly, and this one's gonna be 2 because all of these other heteroatoms are here. And same thing on this side, this is 1 and that's 2. Okay, just because of the identity of all those other atoms. So since all the 1s are on one side and all the 2s are on the other side, that's the same side, or Z. Okay. Yes, we can do E and F. It looks like E and F are weird, but yes. Are we good with that? Okay. And E and F are weird. Why are they weird? All right, so something that you guys should know is, so we have that structure. So this is 1E, okay? And essentially, what you want to do is the same exact thing. Draw this horizontal line, and you guys have to ask yourself, what is the priority of the substituents with respect to that carbon? And they're both ethyls. So can you assign priority to 2 substituents that have the exact same identity? If no, exactly. So there's no 1 or 2 here, so you leave it blank. And here, the same thing, there's no 1 and 2 here because they're the exact same thing, so there's blank. So there's no EZ geometry. So this parallels what we've seen before. When we saw maybe like, we did this with RNS, like I'm just gonna call this like, part of our criteria for a chiral center or a chiral molecule was that it had to have a chiral center in it. And to have a chiral center, you had to have had different substituents, 4 different substituents. And this is kind of an extension of that. Here we don't have 4 different substituents, which is something that you need to assign easy geometry, okay? So it's gonna be the same exact thing that you'll also see in 1F. So 1F looks like this. So you'll need 4 different substituents, okay? So if you notice, I'll just draw the hydrogens here, this hydrogen's here, okay? So with respect to this pi bond, okay, we can definitely do easy geometry, assign priority for the substituents on the right. We definitely have the ketone is gonna be 1, and then that propyl group is gonna be 2. But then same thing over here, we have 2 hydrogens, so you can't assign 1 and 2, you just can't. So because we don't have 4 different substituents, again, no easy geometry. It would be the same thing as saying no chiral centers, therefore a chiral. You guys following that? How do we feel? Good. Okay, got it. This is not meant to be hard. So yes, Caroline, note, if there is not 4 different substituents, there is no easy geometry. No, Caroline, has nothing to do with chiral centers. I was just paralleling the logic, meaning that because there's no chiral centers, it's achiral. Meaning that there were 2 of the same substituents, here, there's at least 2 of the same substituents, that leads me to come to that conclusion, okay? They just didn't explain that in lecture. Oh, any exceptions to the rule? Charles, the exceptions would be 1E and 1F. So the situations where you don't have 4 different substituents, that you just have to know easy geometry. Yeah, this really is supposed to be your easy points on the test. It's like assigning an RNS or like assigning an E and Z. It should be pretty easy. Okay, maybe I'll do one more just to, yeah. Let's just do 1D because it's the last one on the page. Why not? 1D. And we'll just do this. So everyone take a second, try this one out, and do the rules that I said. So step one, you have to draw that horizontal line or diagonal line, whatever you want to call it. Okay, with respect to each of those carbons, you have to assign priority. So let's look at this one first. We clearly see we have a ketone versus a proton, so that's easy. Here again, ketone versus proton, so opposite sides, E. Like 2 seconds. Okay, I think you guys are good at that by now. Let's move on to the next concept. So this is nomenclature. Ugh, I hate this. I'm never a nomenclature type of person, but okay, so let's just do this. So we're on 2A. Okay, so the structure looks like this. Okay, so now before we just had alkanes or haloalkanes. So we've kind of only seen things where, you know, we've had this and we've had branching, and sometimes we've seen some heteroatoms and things like that. But we haven't really seen things with pi bonds or triple bonds, and that's where we're going with this next exam. So this coming exam on I guess in a few weeks is going to be naming alkenes and naming alkynes, and I think you might have a little bit of naming radicals. So you're going to have a lot more functional groups. So the only thing that changes, all the other rules apply in terms of alphabetizing, longest parent chain, yada yada yada, all that still applies. But now we have a new functional group. And you have to number in such a way that A, you include all pi bonds in the parent chain, and B, number that chain in such a way that that alkene gets the lowest number. Alkene is the highest priority, and these 3 dots, I don't know if you guys are familiar with this notation, 3 dots means therefore, it should be the lowest number, okay? The 3 dots in that triangle thing means therefore. Anyway, so those are my 2 guidelines. We're going to do all the things that you've done before, but this time include all pi bonds in the parent chain, and then number that parent chain in such a way that that alkene receives the highest priority, or is the highest priority, which means that it gets the lowest possible number. Caroline, what's your question?
Aren't there also, like I remember seeing in the notes that there are some substituents that work with the pi bond, like vinyl or methylene maybe?
Yeah, there could be vinyl and methyl stuff. I wonder if we're going to see an example of that in these pages. Oh, you mean naming it with vinyl in the name? Are you talking about that specifically?
Like naming it with
yeah. I have never had any Org 1 students like ever had to learn that unless they're adding that this term. So if you see that in the notes, do you see that in the notes somewhere? Because I don't think you guys need to know that.
It's in the notes, yeah.
Oh, okay. So then that's interesting. Can you screenshot it and put it in the chat box, and then I can take a look at it after we do some of these examples, and I can explain this too. So that's a new thing I guess they're adding. Yeah, so somebody just screenshot that, put it in the chat box, and I can probably discuss it with you guys. Okay, so the first thing that we're going to do is, again, number this parent chain in such a way that we get the longest carbon chain possible that includes all the pi bonds. So what we want to do is 1, 2, 3, 4, 5, 6. Okay, I numbered it from right to left because I'm going to get a pi bond that starts at 2 versus 1, 2, 3, 4. Okay, and something that students always mess up with alkene naming is you have to go through a pi bond. So we'll see this again with like specifically like the cyclic structures, and by that I mean sometimes people go like this. They'll start 1, 2, 3, and you can't do that. You have to number in a way that it goes through a pi bond. So 1, 2, 3. Do you see that? It has to go through a pi bond, not start at the end of one. Okay. So you couldn't like this is like a linear is kind of not a good example, but we'll see that in a little bit. So then, based on that whole entire like numbering pattern, you do everything that you've already done. So it would be, we see a 2-methyl and a 5-methyl, so 2,5 dimethyl. Okay, this is 6 carbons. Okay, hex, right? Okay, so I stop there. So before it would have been hexane, right? But now we have an alkene. So these aren't alkanes or cycloalkanes. They should end in enes because they're alkenes or cycloalkenes, okay? So what we do is like, we can't just say hexene because that pi bond could be anywhere. That pi bond could be here, it could be here, it could be there. So we need to indicate with a number where that pi bond is or where that ene is. And it's at position 2. So hex, and I put hyphen 2 hyphen ene, okay? So this would have been 2,5 dimethyl hex hyphen 2 hyphen ene, okay? So everything is the exact same thing, but instead of calling it hexene, don't forget to add this extra number to indicate the position of that pi bond, okay? So I know nomenclature isn't everybody's favorite, but like you can see, it's not too much crazy, too much more complicated, if that's even English. It's not more complicated, basically. You just add an extra level of identifying where that pi bond is. Okay, so B, we'll do another example. So 2B looks like this. So, so I have a question for you guys. Why didn't I say any easy geometry in 2A? If you guys want to put that in the chat box. Maybe you guys didn't catch on, I didn't show any. Exactly, so now you guys understand that. There are two of the same substituents, two methyls, I love that, yeah? So there are, yes, you're right that maybe this on position 3, there's two different substituents, but on position 2, it's two methyl groups. So exactly, same sub, you can't have easy geometry. And just like we saw before with chiral centers and stuff like that, you put R and S like lettering in front of the name. So if I had any easy stuff, I'd be putting it in the front. And clearly I don't have any easy stuff in this name because there is none. And by extension, 2B, is there going to be easy geometry for 2B? Nope. Again, same thing. No, because we have two hydrogens. So don't worry about it here. Great. You guys are awesome. So smart. Love that. 2B. So then the same thing. So we need to number now in such a way that we get the longest. So one thing I also want to mention is you can clearly see 1, 2, 3, 4, 5, 6, 7. Okay, so that's a 7 carbon chain. 1, 2, 3, 4, 5, 6, 7. So actually, in this example, it's not going to become evident, but you'll see there might be an instance where there is a longer carbon chain possible, like maybe like if I added like an extra group down here, you get like an 8-member chain, okay, but it doesn't include the pi bond. Whereas here, if I started numbering from up here, it would be a 7 carbon chain. And we want that carbon chain to have the alkene, even though it might be like a little fewer carbons less, it needs to have the alkene in it, okay? So in this situation, it's not gonna really matter because no matter what, we're gonna get a 7 carbon chain, but the proper way to number it is 1, 2, 3, 4, 5, 6, 7. Again, you have to go through a pi bond. You wanna give that pi bond the lowest set of numbers first, okay? And then now everything else is just gonna be what we were used to. So we have a methyl group on 6, so I'll put an M here. We have a tert-butyl group, okay? Remember it goes by B over there. So by extension, we're gonna say that's 3 tert-butyl, 6 methyl, okay? Hept. Okay, so now here's a specific situation. You can, I always do this because I don't want to lose points ever, but you can technically be lazy if it's on carbon number 1 because it's assumed that if you don't have a number in there that it is carbon 1. So you can just send heptene. But rarely, I will never do that. Even with you guys, I will never do that. I'm telling you, you can, but like, don't. Because it's just really important to always just like, this isn't wrong. Like this is just as equivalent as if I didn't have it. But like, you have to do it for every other thing besides 1, so like a 2, a 3, or 4, or 5, like, you know what I'm saying? So you might as well just get in the habit of always doing it. And yes, I saw that in the chat box. This is also, could have been 3 tert-butyl, 6 methyl, 1 heptene. So you could also put the whole number before heptene as well. I literally always do the top example though, always. Up to you guys, personal preference. Okay, I'm just gonna check what Caroline sent in here real quick. Oh. You will not, okay, so if everybody wants to just download that screenshot that Caroline just put in the chat, this is from the nomenclature. Yeah, you should totally know these names, like 100%. I've never seen nomenclature with this before though, like in the sense of like naming vinyl, naming allylic, naming methylene. Knowing what these are is important for a lot of our discussions that we're gonna have, but we're not there yet, so don't worry about that for now. I really don't think you need to worry about that. Why do we not start numbering at the tert-butyl if it creates more substituents? Okay, so yeah, that's a great question. So essentially what's happening now is with the pi bond, it's a new type of priority. So yes, we typically want to have with alkanes, you know, the longest parent chain with as many substituents as possible, having the lowest set of numbers. But when you start introducing other functional groups like alkenes or alkynes, that whole thing kind of changes. The new rule now is what matters the most is that this pi bond gets the lowest set of numbers, not do I have the most like substituents, okay? So the rules kind of change slightly when you get more functional groups. I don't know if that matters. Are you talking about the allylic and vinyl stuff? Because I really had never seen that before until now. Oh, okay. Let me get back to you. I'll talk to Dr. Peterson. I'll text her after this and see if like that's a thing that's going to be expected to be tested. Seriously, it's the first time I've ever seen it. It was only one question. Okay, cool. All right, so I think that's good for 2B. 2C. Okay, let's just do 2C. Actually, no, let's move on. Let's do something more complicated. Let's do 2D. Okay, so we have some crazy looking structure. So we are here. Okay, so this is something that you guys could very well have on your exam. You probably will have on your exam because it combines your RNS, knowledge, it combines your EZ knowledge, and it also combines your just overall nomenclature knowledge. So what you want to do is again, you want to number in such a way that you give your you give that alkene the lowest possible set of numbers. So if I start from the left, it's 1, 2, 3, 4. If I start from the right, it's 1, 2, 3, 4, 5. It could also be 1, 2, 3, 4, 5. Okay, so my guess is I'm probably going to start with 1, 2, 3, 4, 5. 1, 2. I like this way better. 1, 2, 3, 4, 5, 6, 7, 8, 9. Because it gives me the longest carbon chain. Okay. So I could have basically started from up here. That's what I was kind of thinking about, because no matter what, I would have gotten 1, 2, 3, 4 for that pi bond. And over here, I got 1, 2, 3, 4. But the reason why I started left to right, as opposed to right to left, is I get a nonane, versus this way I would get 1, 2, 3, 4, 5, 6, 7, 8 in octane. Okay. So that's why I numbered it that way. Anybody have any questions on that? Yeah, Jacob, you can't start at the wedged methyl, because if you did that, it would be 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you get also this we're indicating chirality here as well, Jacob. So this is probably going to be a good hint that you're going to have to assign this as it's a substituent, like R methyl, something like that. It's viewed whenever you see this wedge dash thing, it's typically a good idea that it's typically like a big indicator that it's part of a substituent on the chain. So we think about first methyl over methyl. Okay, so we still want the longest carbon chain. Typically, if we can do that, yes, Jacob. Appy, no, because the ethyl is part of the longest chain. Yes, you got it. Thank you for clarifying that, Appy. Okay, so in terms of naming everything else, we have methyl and methyl, okay? But clearly, we have to consider RNS and E and Z and all that stuff. So let's do RNS for position 3. If I'm assigning, priority to these substituents, I just immediately see 1, 2, 3, like in 2 seconds. I hope you guys can see that too. Like clearly, this right whole carbon fragment is a lot. This is an ethyl, and that's a methyl. That like really easy. So 1, 2, 3. That goes to the right. The 4th group is oriented on a dash. Okay, so that is R. Okay. So we try to number the double bond with the highest priority, meaning lower set of number. Correct. Yes. And then look for the longest carbon chain. Also correct. Good. All right. So that's that one. And then for this position at carbon 7, we see we have obviously this whole left fragment. Okay, which is clearly higher priority. 1. Ethyl is higher priority than the methyl. 3. So tracing that gives me S. Right? Do you see that S? But don't forget, your 4th priority group was on a wedge, so you have to remember to flip. So this is R. Okay, so both of your, chiral centers in that molecule are going to be R. And then now we also do the final thing. We have to consider easy geometry through this alkene. So now if we're looking here with respect to each of these carbons, we see we have carbons on one side and then protons. Carbons on one side and protons. So if I were, to assign configuration here or priority here, it would be 2, 2, 1, 1. So that's the same side, and this would be Z. Okay, so look at all that craziness, and that just told me the stereochemistry of everything that's in here. Okay, so now we're just going to put all of this stereochemical information in the front of the name. So something that's super important. So if you're falling asleep, wake up here, EZ geometry has to go in front of RNS, goes in front of RNS. It's just convention. So just remember, like logically, it's so easy to remember to put EZ before RNS and never forget it. It's so easy to put EZ before RNS. Okay, so essentially, I'm gonna put in front 4Z, okay, because that's just convention. The EZ stuff goes before. Then 3R, and then 7R, okay, and that's in parentheses in the front of my name. So that is, these parentheses in the front is supposed to be, inclusive of all of the types of configurations that you see in your molecule before you even get into the name. So Jacob, when we said the EZ stuff, and when we couldn't classify that, it was when there were two protons or two hydrogens on the same carbon, meaning hydrogen here, hydrogen there. Oh, you can't really see that. Hydrogen here and hydrogen there, not on opposite carbons, okay? And, okay, I think I just answered that to Jada. With that example we were seeing before was something like this, like where one carbon had both of those. Because, we do one carbon at a time, and we're looking with respect to that one carbon, where are those priorities aligning? Is it there's one up here, two down here? And with this specific configuration, when they're both the same thing, you can't do that. You can't do like 1 and 2 because they're the same thing. So there's no EZ geometry. Here, they're on opposite carbons, so you definitely can assign EZ there. Yeah, good. Okay, so then with the rest of the name, you have to basically just indicate, where everything is. So we see we have a 3 and a 7 dimethyl. Okay, so there's 2 methyls there. And then non, okay, hyphen, where was the beginning of that alkene? 4-ene. And that's the crazy name that you guys get. Okay, so you can see it's pretty similar to what you've seen before. Just a couple of new caveats is that EZ always goes before RNS. RNS is not going away. Keep practicing all that stuff. And you want to have your alkene at the lowest set of numbers possible, and also try and find the longest carbon chain if you can. Yes, you always do RNS and E and Z if it's applicable. Yes, Claudia, thank you. That's exactly what we're saying. Okay, so that's 2D. I'm gonna do one more example, then we gotta move on to like reaction stuff. So let's do a cyclic example. Let's do 2H, okay? So I think 2D is probably the hardest you can get. That's something with chirality, EZ, things like that. So this is definitely like probably one of your harder ones. But let's go to 2H, okay? So actually let's do 2E first, and then we'll do 2H, and then we'll move on. So 2E looks like this. So 2E, and is anybody in Orgo lab this semester? Anybody in Orgo lab? I don't even know if you guys can do that as an Orgo 1 student, but I work in the Orgo lab. I make some of your chemicals and stuff, so that's cool. So you guys will see me next semester if you guys are taking Orgo lab. I also work there. And this is one of your molecules that you guys will be extracting from oranges. It's called D-limonene. And ene may be indicative of that. So this is what like the citrusy smell. This is like really cool. So this is the molecule, if anyone cares. It's an oil. And what you want to do is you want to name this. So how do I number around this cyclic structure in a way that I give my alkene the highest priority, meaning the lowest set of numbers, and I also account for that isopropyl substituent. So I would basically number it like this: 1, 2. So you have to go through the pi bond to give it 3. A lot of the times people will do this, and this is like, I'm happy I'm saying this now so you guys don't do it. People will do this 1, 2 because they want to give that substituent also the lowest set of numbers, and you have to go through a bond, okay? Through the bond, 1, 2. So no, that's not right. So that's pretty much all I need. I know it's a 6-numbered ring, okay? And let's just kind of indicate. And also another thing, there is also, if you're sleeping, no EZ geometry in cyclic structures. Because you can't, and the reason that is, and that's logical, is you can't get like, there's no other orientation. Like you can't like rotate a ring to get like a trans format. Like it's very easy to do that versus rotating it to get that or something like that, like 2 different configurations. Well, I'm sorry, not rotating, but you can get 2 different configurations there. Here, there's nothing you can do. Like, I don't know another way to move this ring to get like another version of that. So there is no easy geometry in cyclic structure. So that's something you can kind of avoid. That's good. But we still have to do RNS. So to me, it's pretty clear that this is going to be priority number 1 on the right. This is going to be priority 2 on the I'm sorry, number 1 on the left, 2 on the right, 3 above. So tracing that, that is giving me the S configuration, I believe. Did I do that right? Wait, hold on. Carbon, carbon, carbon versus, oh, I did this wrong. My bad, my bad, my bad, my bad, my bad. Okay, so what it should be is 1 because it's carbons with other carbons. Okay, this is carbon, hydrogen, hydrogen. This is 2, that is 3. So that gives me S. Wait, why am I getting S? Hold on. 1, 2, 3. 1, 2, 3. Getting S. Are you guys getting R? Is anybody getting R? Madison, how are you numbering it? Because it should be R. I know that, but you think the double bond is 1. Ooh, carbon. Oh my God. Great. I'm so happy I did that. Yeah. Thank you, Madison. That was awesome. I just totally forgot about that. Okay. So something different, and this is exactly something I messed up on, so hopefully you guys don't mess up on it, is when you're doing RNS with these like pi bonds now as being a part of like your substituent, we call them, it's something called phantom atoms. I don't know if you guys have ever heard of that before, phantom atoms. And like what you basically say is, this is right here, this is carbon attached to a carbon, and then it's because there's the pi bond here, you basically say it's attached to another carbon. So that's this is what we call the phantom atom. Kind of cool. Like Danny Phantom, anybody's watched that? Like, you know, like as a fetus all the way back then. Yeah, Danny Phantom. So it's the phantom atom because it doesn't really, it's not like a whole nother entity. Like it's just because there's a pi bond there, it's a way of us saying like, when we're doing these comparisons. So that's the left side. So the right side would be CHH. Okay, do you see that? So CHH versus CCC. Do you see how I'm drawing those lines? CCC versus CHH. Okay, so that's why we call this the phantom atom, because it has an extra double bond there. So yes, this is why, and then if you did this from up here, this one would be C, and then there's an H, and then other C's. So C, obviously C's, and then another H, okay? So these are like what I'm comparing to, it looks like, okay? So this one would be 1 on the left, it looks like 2 up top here, and then 3 to my right, there we go. And that would be R, okay? Sorry about that, so that would be R. Thank you for the help, I appreciate that. Okay. Okay, let's see what the questions are. When just be CH. Abby, thank you. Names the phantom atoms. Mary, for the cyclic rings, can you assign the EZ when the rings have more than 7 carbons? No. Caroline, wouldn't the one on the bottom be CCH? But isn't the extra C the phantom? So for me, it's C. Like that's the first carbon right here is where my pen is. That's C. The first carbon, which is the one that's attached, and then I write this extra one because of the pi bond. That's the phantom thing there. Okay, so that's this guy. Okay. So no, it shouldn't be CCH, it's CCC. And that's how you get R. Okay. So then essentially what that means is we are going to say that that's 3R, okay? 3R, 3 isopropyl cyclohexene. And you don't have to, you know, say 1 in this situation because it's already understood that in these cyclic structures, you're always numbering it as if it was 1, as that alkene being 1. Okay, it's always understood in cyclic systems. Okay. And one more thing. So whether or not you put 3R or just R, oh, thanks. Wow, there you go. It's funny, someone stuck in the chat box. Whether you say 3R or you just say R also doesn't matter. I always say it because I don't, like, less is not more, okay? More is always good here, okay? So like, you should be always saying where that number of the stereochem is. In this case, you can get away with not doing it because there's only 1 chiral center. Same thing with saying 1 here. Like, these are all the things, okay? So like, you don't have to. I would, just because But like, why not? Okay. That's that. Okay, so that's I'm kind of gonna leave that there.
Hey, Stephen, can I ask you a question?
Yes.
So what I was saying was that like usually in her or in the other problems when we used to do RNS, like she would look at what was attached to the like adjacent carbon. So that's why I thought the bottom one would be like two C's and then an H, and then the right one would just be C and then two H's, and the top one would be.
So you're doing like C, C, and there's an H there? Is that how you're doing it?
Yeah, like instead of counting the one that's like adjacent to it, you count what's like attached to that adjacent carbon. So it
Yeah,
would
so
just
this
be
is
like,
the adjacent one, and you're counting what's attached to that point, what you're
right.
saying? Yeah, so you're doing basically, there's a C, an H, and like another C. So that's what you're saying. That's not what you want to do here, because there's something different now with this extra pi bond. You don't want to, like, that proton that you're saying, I hate doing this method. Like but essentially it's, you're right. Same thing with what's attached to that adjacent carbon. So carbon, but this pi bond takes priority. So that's why you also say this other carbon, okay, as well. That's that other thing. And I guess you're saying this other hydrogen, but the other carbon takes priority over that. I don't know. This is starting to get messy. I don't really have a good explanation for you, honestly. I just like, to me, I just saw carbon, carbon, carbon. Even though I know there's a proton there, I'm kind of ignoring it. And I don't really have a good answer why. I don't know. I just think something else is happening with this pi bond. Dr. H went over, what did it say? Dr. H went over Fannerman's lecture 7. Yeah, maybe check that out, because I don't really have the best explanation of why I do that. I just know to, like, if I see a choice of like listing 3 carbon atoms in a row versus like CCH, I'm going to pick the carbon, carbon, carbon one. Yeah. Okay, cool. That's enough for now. Let's move on past nomenclature. So let's just kind of finish there. So that was chapter 5. Oh, we didn't do a diene example. Let's just do 2H, sorry, and then I'll move on, I swear. 2H. Okay, so here we have okay. So there are instances where we can have more than one pi bond, so dienes or trienes. Okay, so those exist, and you guys will be required to name these. But for 2H, same thing. So we want a number in such a way that we go through this bond, okay? And we want to give also the lowest set of numbers to our substituents. So it looks like, oops, sorry, I got a FaceTime call. Okay, so through this bond, it looks like we can do 1, 2, 3, 4, 5 for the isopropyl, or it looks like I can do 1, 2, 3, 4, 5. I'm liking, I like this, and maybe this won't be so clear for you guys. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Actually, no, I don't really like that. 1, 2, 1, 2, 3. I like this one. Okay, so let me do it in purple. 1, 2, 3, 4, 5. I like that one. Okay, so the reason, so you can see, like, even I don't get it right on the first time sometimes. Like, I have to like just kind of play around and like see which order goes best. But I like this way because I'm giving this methyl group literally number 1, so that's good. I'm also giving this first pi bond number 1, and then I'm also giving the next pi bond number 3. Okay, really quick. So it's 1 and 3, and I'm also giving these 2 substituents 1 and 3. So that's definitely like the best option. Okay, so in order, we have no easy geometry or RNS to consider, so it's pretty easy. So it's methyl, methyl, and isopropyl. So we want to do 3 isopropyl, okay, 1, 5 dimethyl, everything is the same. Okay, cyclo, okay, here's where it gets a little bit different. We used to say like, cyclopentene, okay? This time you have to have penta, okay? So whenever you think diene or triene, just like think about exhaling air, like A. You have to remember this A. Like, you will get points off, and I 100% know it's going to be like a trick question. It's not pentene, it's penta, okay? You get this extra A, and it's, where are the positions of those pi bonds? 1, 3, 1, 3, diene, okay? Penta, 1, 3, diene. And you have to di to indicate 2. So that's the one extra variant of this. Whenever you have diene or trienes, you have to have a there. So like 1, 3, 5 triene, or 1, 3 diene, okay? So yeah, that one is spicy. Anybody know that? Like drinking soda, like the dog. Why is it spicy? I don't know. It's getting on my head. All right, so that is nomenclature and easy geometry, okay? So that was all chapter 5. Pretty easy points on your test, I feel like. Let's move on to chapter 6. Okay, I'm excited. All right, we are finally here. The beginning of organic chemistry for real this time. And I really like this stuff. There should never be a point throughout like anything that I explain to you guys that you don't understand. And if you're trying to memorize it, that you're not understanding it right, okay? So stop me if you don't understand it. I will make sure that you guys understand the chemical logic, because then there's zero memorization. This is the point where everybody, you know, when you hear like that, like famous line that "or goes the killer," everybody says that this is the part that's the killer. And like, it's not, it really isn't, okay? So we're on chapter 6, and we're gonna do our first reaction, and it's called hydrohalogenation. Hydrohalogenation. And this is just like regular notes. I'm not like copying this anywhere. So actually, I have to talk about carbocations. I'll do carbocation stability later. Okay, hydrohalogenation, okay? So what does that mean? So we have something hydro and something halogenating, okay? So what do we think? Hydro sounds like hydrogen, and halogen sounds like halogen, so hydrogen. This sounds like halogen. So maybe something like a hydrogen with a halogen, where X is the halogen, is what I'm talking about. So yeah, this is going to be my reagent. This is the first reaction we're ever learning. Okay, so our reagent or our reactant is going to be some sort of hydrogen halide bond. Okay, that's the reaction, hydrohalogenation. Okay, so examples of that would be HBr, HCl, HI. Okay, because hydrogens with these halogens attached to them. Okay, and there's a specific consequence. You guys know this actually at this point. Why do we think we're using these reagents at this point? Like, what is characteristic of all these bonds? Okay, and it's one word I'm looking for. I'm not going to say what it starts with, because I feel like that would give it away. But there's something about these bonds that, or like these structures. Okay, acidic is one thing I like. Okay, there's another word that I'm looking for that explains why, something that's going on in this, in all these molecules. Ooh, polar, I like that. Okay, I was looking for dipole, but polar works. So dipoles and polar and polarity, and there's a reason why organic chemists use this solvent. Use this reagent, excuse me. Okay, so let's take an example of that. Let's take HBr. Okay, so for HBr, let's draw the electron cloud. And I think you guys have seen me do this before when we did acidity. Okay, and this is literally meant to be like the valence electron mapping, basically, of like where all the electrons are localized at any given point. And because there's a localized dipole moment towards the bromine, because for reasons we talked about, having, you know, more protons in terms of atomic number, it pulls more electrons towards it. So we're going to accumulate at any given point more electrons on that side of this bromine. So there's a whole bunch of electrons, a whole bunch of electrons, a whole bunch of electrons, okay? And that makes this side partial negative, so it makes that side partially positive. Okay, so it makes sense, you know, that we've been talking about alkenes. So, you know, your starting material, you always need some sort of starting material, and that's going to be an alkene. So let's just say it's some sort of alkene, okay, plus one of these reagents, gives me some sort of product, okay? So that's my main reaction so far. So let's kind of do an example of that. Let's say I have butene, okay, trans 2-butene, and I am going to subject it to something called hydrobromic acid. So it's the hydrogen halide, okay? So that's literally the only reaction we know so far. So this is different than what we've seen before. We haven't really done this. So what happens when I take this, you know, trans 2-butene molecule, and I subject it, and I throw it into a flask with hydrobromic acid? So something you guys should know about, and I think we've done this before, I'm going to rotate, okay? Do you see this? Actually, do you see this trans 2-butene? I'm going to rotate like this, okay? So essentially, this is equivalent to drawing a structure that looks like that and that, okay? But what is this pi bond? What specifically, remember, in terms of orbitals, what was that pi bond? Well, in terms of orbitals, it was these, you know, unhybridized p orbitals that had a pair of electrons in them, okay? And notice, remember we said also back in acid-base chemistry, we said that, remember, the more S character, remember percent S character, the more electronegative it was. Oh, I mean, increasing percent S means increasing electronegativity. And the rationale was the S orbitals are very concentrated towards the center, whereas these kind of p orbitals are kind of higher and above that plane, okay? So they're like not as tightly bound, or they're not as electronegatively attached to the molecule as these p orbitals are. So that makes sense that the p orbitals in this pi bond, okay, is a source of electrons or a source of negative, charge that maybe wants this positive charge, okay? Does that kind of make a little bit of sense so far? The pi bond's electrons are a little bit higher and farther away than like the main sigma bonding framework. So that means that they're more reactive. They're not as tightly bound to that molecule, and they can maybe like attach on to a positive thing that we see up here, okay? So maybe this logic is kind of helping you out with understanding the rationale here. So our mechanistic arrows, so this is now we already saw, with acid-base chemistry, so this might be, familiar to you guys, but we have a source of negative charge grabbing a, sink or a deficiency, some sort of positive charge things, okay? And then a bond is going to break, okay? And the bond between, the hydrogen and the bromine, there's electron density is going to be retained on the bromine for, I believe, reasons we've talked about before. Bromine is so electronegative, so it makes sense that electron density within that, polar bond at first stays with the bromine. Okay, so sorry, my phone is. Okay, here we are. Okay, so what is the result of that step? So the result of that step is a structure with something called a carbocation. Okay, so notice how this pi bond, okay, grabbed this proton, okay, and we formed a new carbon-hydrogen bond. So let's say that the two electrons in here took that one proton. Remember, both those electrons stayed on the bromine. So these two electrons in this pi bond formed a carbon-hydrogen bond right here. That's this carbon-hydrogen bond, okay? And then because we took electrons away from this other position, this other carbon, before, that's all it was. It was two carbon bonds and then a proton, so that was 6 valence. And we still have that there, but it's 6 valence. So that's why it gets a positive charge. So this is called a carbocation. And on Wednesday, we're going to talk about stability of all of those carbocations and different types of products we can get there. But essentially right now, this is all we're left with. We're at this secondary carbocation. And then what was also the result of that step from this reagent? Well, we had free bromide. So by free bromide, I mean it's a complete octet anion, okay, bromide, okay? So what do we think is the next chemical step in terms of these electrons? Well, we have some sort of source of electrons. We have some sort of sink of electrons, okay, so this positive, molecule, positive charge. So it makes sense maybe for the next arrow to do that. Okay, so the result is now we keep this carbon-hydrogen bond that we formed from step 1, and then now we have this new carbon-bromine bond over here. Okay, so that is, my structure. But, something we need to talk about is, did we generate a chiral center? Yeah, we generated a chiral center. So we have a new center right here with 4 different substituents. So we definitely have to take into account the major stereoisomers. You guys are probably like, ugh. The major stereoisomers that we know that arise from, having chiral centers when we're doing these reactions. So essentially, if we generated a new chiral center and there's one chiral center, I expect 2 major stereoisomers. So I should expect both enantiomers as products in this situation. So how do I know that? And where's that logic coming from? Well, let's go back to this intermediate. So this carbocation is also called an intermediate. So it's something that's created in the middle of the reaction, but it's not isolated product. It is basically created at one point and then used up the next. Okay, so carbocation and intermediate. Okay, so essentially, if I were to consider the hybridization of this carbon right here, this carbocation, what is the hybridization scheme in the chat box? What do we all think for this carbocation? sp2? Is that what we're thinking? Jacob said sp2. Anybody else? Crickets. Yes, it's sp2, okay? So it's sp2 because I see 3 areas of electron density. So remember what sp2 means. It means you have these like trigonal planar, like, you know, sp2 orbitals, and then you had perpendicular, okay? So I'm just gonna draw this again. This would be like a carbon-carbon bond. And then you had perpendicular, this is the p orbitals, okay? So the same thing is here, and you guys can't see this, but there's this unhybridized p orbital right here. So this bromide could either have come on the top, okay? And if it came on the top, maybe that'd be corresponding to that wedge. And it could also have equally likely have came on the bottom. And maybe if it came on the bottom, it would have been the dash. So do you see that? How, I'm gonna draw the hydrogen here just so you guys remember. But you can see how with this unhybridized p orbital, the bromine could have equally as likely have come from the top face of that lobe, forming the wedge, or the back face of that lobe, forming the dash, okay? So that's why these would be both of my products, okay? So this is the first reaction you learn. You can tell like this is very different than what you're used to. I like this a lot more because it literally makes perfect sense. I hope every single part of this like mechanistic rationale made sense. Are there any questions so far in terms of like, how do I know this orbital does this? And you don't have to know it in that great detail. I just think that it's like, it helps you, I think, in knowing that. Caroline, what's up? Oh, it helps, cool, yeah. I think it just helps a little bit more because you know that. How do you know it again? So again, you know pi bonds form from p orbitals. P orbitals are located higher up than s orbitals, which means that they're more reactive typically. And that makes sense. So all of chapter 6 in our workbook is going to be reactions of alkenes because of this very property. These electrons in the pi bond are a little bit higher and less bound to the molecule, which means they're more reactive, and they can react with other reagents and form other molecules. So basically what I would write in the back of your student workbook, if you guys have it, is something like this. You know, hydrohalogenation is our first reaction. We have an alkene, we have to have some sort of hydrohalogen like HBr, and you're going to form some sort of alkyl halide, which is also known as a haloalkane. And here's an example. So, you know, this pi bond is going to grab the proton, you know, generate free bromide. You get that carbocation at that position, and then the bromide comes in and attacks. So just maybe a quick note to tell you what this reaction is, what are my 2 starting materials, what's my end product, and maybe knowing the functional group names helps you out, okay? So definitely start keeping track of this. I think there are going to be 10 reactions in chapter 6, 10 more reactions in chapter 7. So you guys are going to have 20 total reactions on this exam number 3. Okay, so 20 reactions. So, but don't worry, because most of the alkyne reactions, the 10 more that we're going to see in chapter 7, are pretty similar to the chapter 6 reactions we're doing right now. And I think you guys still want this, yes, so something like that. You guys can also screenshot. I mean, yeah. Oh, I see. Yeah, Caroline, I got you. 1 second. I see what you're saying. So whenever you have that unhybridized p orbital, you can either attack from the top or the bottom. And that was pretty obvious, pretty much obvious. So again, like here's the depiction. Like you have this p orbital and there's 2 lobes. It's like, this is like not the best orientation because it's like, here. So look at this. This is like a better example. Like, even though, actually here, look at this carbocation intermediate, and I'm gonna do that same thing. I'm gonna take it and rotate it like that. Okay, so essentially it looks like that, and it looks like that. Okay, so literally all I did was take that and rotate. Okay, so what does that mean? Well, now I have this, let me just draw it as one big conglomerate. So it'd be the 2 p orbitals left and right mixing together. And I'm just gonna like phase it so that you guys can tell like they're different phases. So this is coming from the p orbital here and the p orbital here overlapping, essentially. It's constructive interference. Whatever. The point is you now can see that this is like flat. This is like this. I could have had bromide as my pen come in and attack here, okay, which means it's a wedge, or I could have it coming on the back face, which means it's a dash, okay? So if it's coming from the top face, it's gonna form a wedge. If it comes from the bottom face, like down here, it's gonna be below and into the page. That's bromide. That's a dash. So let's do that. So in this situation, if you don't believe me, let's say I'm gonna have it come and the carbocation's here. Let's say I have, actually I drew it here. It doesn't matter, but I'm gonna draw it here, okay? Carbocation's there. Bromine is gonna come on and stick at the top. So I'm thinking something like that. So bromine, and remember I rotated this before, and it could have equally have likely it came on the bottom face of something down there. Whatever, I remember I rotated. So now rotate it back, okay? So if I rotate this back, that arises. Okay. Do you see that if I rotate forward? If you rotate this forward, like remember this is, oh God, how do I do that? This is already in plane. So if I rotate it forward, the bromine can come out as a wedge. Do you see that? And the same thing down here, the bromine could have came below and rotating it up, it would have been a dash, okay? So that's just kind of like the logic going on there. Hopefully that helps you. I don't know. Let's do, oh, we're out of time. Is it more about the pi bond, p orbital, not the specific sp2 orbitals? Yeah, exactly. You don't worry about the sp2 orbitals at all. It's all really dealing with these p unhybridized p orbitals. That makes sense. These p unhybridized p orbitals. It's redundant, but okay. So let me just do one more example, and then I'll let you guys go. Let's do. So I'm not really following the workbook right now. I'm just kind of like doing this logically with you guys. Let's do this example. So I'm going to treat that with HCl. And there are some other things that we have to obviously consider, but we'll deal with this on Wednesday. We have more than enough time. So you guys kind of understand all the logic, and you don't have to go through all of this rationale every time. I just did it for the first time so that you guys can like really understand what's going on here. You should understand every step. And you know that this pi bond with these electrons in this specific pi bond are localized a little bit higher and farther away than the main sigma bond framework, so that their negative charge is above here. I can kind of grab this polar proton that's positive because of the dipole moment. So I'm thinking that's my first step. And you know, in this situation, we don't have any regiochemistry to deal with yet, which will be a situation we'll deal with on Wednesday. But essentially, we basically can put the carbocation in either place for all intents and purposes right now. We'll discuss more later. And we generated free chloride. Okay, so this should make sense. This is my carbocation. This is my intermediate. This is the thing that has the unhybridized p orbital now. So I can either attack from the top as a wedge or attack from the bottom and form a dash. Okay, and remember, it makes sense that this negative wants the positive thing. Okay, so your structures should be something that looks like either a wedged chlorine or a dash chlorine. Those are your two major stereoisomers, okay? So that is the first type of reaction we're dealing with in Orgo 1, taking an alkene, subjecting it to some sort of hydrogen halide, and then forming these haloalkene end products, okay? You don't have to include the proton in the final structures, and you shouldn't. I'm just doing it right now because you guys are very introductory into these reactions. So you guys can see that there is definitely a hydrogen bond forming adjacent to a chlorine bond forming. That's the only reason why I'm putting that in there. Okay. I'm going to leave you guys there. I think we did enough today. So just recapping, we went over all of easy geometry, pretty easy. Remember, you need to have 4 different substituents. The next thing you need to do is know how to name things, know how to name dienes with that extra A, know how to name trienes with that extra A. And again, you have to go through those pi bonds. That's another thing that you get to remember. And then we talked about this hydrohalogenation reaction. Pretty self-explanatory so far. There are some more things that we need to talk about with this in terms of regiochemistry and carbocation stability, but we'll deal with that on Wednesday. All right, so good luck, and I'll see you guys then.